Welcome. This is our second day of talking about support vector machines. So on the first day we talked about hard margin SVM, which separates classes with a hyperplane. We also talked about soft margin SVM, which isn't required to separate the classes but still uses a hyperplane as its decision boundary. And today we're going to talk about kernelized support vector machines, which allow us to think about curvy decision boundaries. As motivation for this problem, suppose you get the following training set. You have the blue points here and the red points here, and it's pretty clear visually that there's a good way to separate blue from red, actually completely in this case, but it's going to require that we use something other than a plane because the data are not linearly separable. If we think back to our high school math class, we might remember that there's a conic section that has this shape. And if we can come up with the equation for that conic section, then that might give us a good way to detect which side of that boundary a point is on and thereby declare it to be either red or blue. So the conic section that has this shape is of the form x squared minus y squared equals a constant. So let's define a map phi, which sends x comma y to x squared minus y squared, let's say minus 1. And what we can see is that this does separate red from blue, although it comes very close to missing several of these blue points, so we might scoot it over a bit to get more of a margin. So what we can do is calculate x squared minus y squared and check if it's bigger than 0.5. If it is, then we're in one of these blue regions, and if it isn't, then we're one of these red regions. And if it's exactly equal to 0.5, then we're right on this boundary. One way to think about what's going on is to lift these points using the map into a three-dimensional space. So for a given ordered pair x comma y, let's look at the point in R3, x comma y comma x squared minus y squared. And what we see is that the points are actually linearly separated in this space. If we angle our view just so and zoom in, we can see that there's a horizontal plane in this picture that separates the red from the blue. So if we can come up with such a map phi that sends our ordered pairs x comma y into some higher dimensional space, then we stand a better chance of finding a hyperplane that does a nice job of separating the points. And even if it doesn't separate them perfectly, as it does here, it still might correspond to a curve in the original space that does a better job of acting as a decision boundary. Clearly, we don't want to be reliant on our 10th grade algebra skills to think of boundaries that are going to separate various clusters of points. This needs to happen more automatically. And it turns out there's a very nice way to do this that involves not even having to think about the map phi. But to develop this idea, let's take a step back and just review the dual formulation of the soft margin linear SVM. So if you recall, what we do is solve the constrained optimization problem, which asks us to find the maximum of the sum of eta minus this quantity, which is obtained by calculating minus 1/2 eta O dot y transpose x transpose eta O dot y. And the constraints are that the weights eta have to all be between 0 and c, and they have to dot with y to give 0. So visually, what ends up happening when we solve this optimization problem is we end up with 0 weights at every point that's on the safe side of the slab, and weights of capital C at every point that's inside the slab or on the wrong side, and the ones that are right on the edge can be between 0 and c. And these weights have to total up to the same amount on all the red points as all the blue points. That's what's represented by this equation eta transpose y equals 0, because the entries of y, the response vector, are just +1s and -1 depending on whether the points are blue or red. And when you dot such a vector with another vector, it's going to sum all of its components in the positions corresponding to the positive ones, also sum all the components in the positions corresponding to the negative ones, and subtract. Once we solve this problem, we can come up with a value of beta by computing x transpose eta O dot y. And then we can get alpha back based on the observation that if eta is strictly between 0 and c for a component, it's right on the boundary. So once we know beta and we know a particular point that's on the boundary, beta transpose x equals -1, then we can just solve that equation for alpha. It's going to be the y value, whichever it is, +1 or -1, minus beta transpose x. And finally, to return a prediction, we just detect which side of the midline we're on. So we just compute beta transpose x plus alpha and see if it's negative. If so, we're over here on the negative side. If it's positive, then we're over here on the positive side. So the prediction function is the sine of x times beta plus alpha, where x is a row vector representing a test point. So like if x were here, we would return negative because x beta plus alpha is going to be negative on that side of the line. So suppose we take every row of our matrix X, so it contains training observations in the rows, and we replace it with the matrix we get when we apply phi to every observation. So phi is some map that's taking our original space into some other space, typically a higher dimensional space, although it could be the same or lower. And we want to see how this changes things. And the first thing to observe is that X almost only ever appears in this story in the form XX transpose. And XX transpose is the matrix of dot products of rows of X. So if we define a matrix K, called a kernel matrix, whose ijth entry is just phi of the ith row of X dotted with phi of the jth row of X, then what we can do is replace XX transpose with this matrix K. And then we continue to follow the story, and we see X showing up again here in the form of X transpose. And to write that down, we would need to know this transformation phi. But let's just keep going. We might not be interested in beta because it does pertain to the separating hyperplane in the higher dimensional space. And we're hoping here not have to worry so much about phi. So let's keep going. We see X again here, but X also appears multiplied by beta. So what we can do is substitute for beta here. And what we see is that once again we have XX transpose showing up. And if we have K, we can substitute there as well. And then finally, we again have an X showing up here, as well as beta, which we're trying to punt on. However, what we can do is substitute for beta again, and we have another one of these XX transpose operations. This one's different though because X is a test point. It's a new point where we want to assess, do we think this is blue or red? So it's different than the original matrix K, but it is very similar. So I'll call this one K test. And this is going to be a row vector consisting of phi of x dotted with phi of xj as j ranges from 1 to n. We take our vector where we want to make an assessment, we take all of our training observations, we apply phi to them, we dot the results, and that gives us a row vector, and then we substitute that in here. And the point is, we never need to know phi to do any of this stuff, as long as we know how to dot images under phi of vectors in our original space. So in other words, phi shows up only in this particular combination. And if we have this function k, which is called the kernel function, then we don't need to worry about phi anymore. We can work out this whole process without ever thinking about this map phi. And that's pretty amazing because that means we're going to be able to find curvy decision surfaces in our original space by implicitly mapping to this higher dimensional space with this map phi without ever thinking about the map phi at all. And you might think it's going to be quite tricky to work out what this function k is without thinking about phi, but actually there's a theorem that allows us to just throw in the k that we want and know that there is some phi that corresponds to it. So some example kernels, like the polynomial kernel of degree d, which is equal to gamma times x dot y plus r all raised to the d power. And here, gamma and r are hyperparameters that can be set. There's also one involving a Gaussian, which is called a radial basis function. And here are a couple of facts about the connection between those kernels k and their corresponding maps phi. x1.x2 plus 1 squared, so this is the degree 2 polynomial kernel with gamma equals 1 and r equals 1, corresponds to this map from 2-dimensional space into 6-dimensional space. So we get a constant feature, we get the 2 original features scaled by some modest scaling constant square root 2, and then we get the 3 quadratic combinations of the original regressors. In other words, just using this kernel function gives us the same result we would have gotten had we augmented our feature space with quadratic combinations of the regressors, assuming we included these particular constants. And the radial basis function actually corresponds to a map from your original feature space, let's say RP, to an infinite dimensional vector space. So it's really important for this function that we don't have to deal with the actual map phi because it's not possible to work with it computationally. Nevertheless, we are finding a surface which implicitly is what you would get if you applied this map to this infinite dimensional space and looked for a separating hyperplane there. And just as a note, the condition on k that ensures that it does correspond to a map phi is positive semi-definiteness, which means that if we take any list of vectors x1 up to xn and form the matrix that we get by applying k to pairs of them, that matrix is positive semi-definite. And it can be checked that this property holds for the polynomial kernel and the radial basis kernel. So let's actually implement this thing. The first step is to define a struct that's going to correspond to a support vector machine. So it's just an organizational tool for keeping all this data packaged together. So we're going to have an x, a y, an eta, and since this is going to be a kernelized vector machine, let's take out the beta. We'll have an alpha. We decided we do still need that. We have a C value corresponding to the penalty for the soft margin SVM in the higher dimensional space, and we'll also have a kernel this time. So the kernel can either be the radial basis kernel, as we discussed, or the quadratic kernel that we discussed, or it can be a linear kernel, which corresponds to the identity map phi. So if you do nothing to two vectors and then dot them, that's the same as just dotting them. So this allows us to recover the linear soft margin SVM as a special case of this kernelized SVM. And we define a method for the SVM constructor that takes a bunch of keyword arguments and will supply missing values for things, or in the case of the kernel, a default of the radial basis kernel, or for C, we'll give a default value of 1. And these eta and alpha values are going to be filled in by the fit function. So we come up with our number of training observations and our number of features based on the feature matrix X belonging to the support vector machine S. Then we set up a model for jump, and we associate some variables with it. We'll need a bunch of etas, one for each training observation, so that's from 1 to n rows. And we need an alpha value. And the next thing we're supposed to do here is define kernel matrix K. So we'll just do exactly what it is that we're supposed to do. We'll iterate over the rows of the training matrix. And for each pair, row 1 and row 2, we'll calculate the kernel evaluated on those 2 rows. Next, we set our objective function. Then we'll optimize our model, extract the fit value of eta, and then we have to come up with alpha on our own. But we have a strategy for that. We check every place where s.eta is between 0 and c. Find the indices where that's true. Let's call this end. So this will be a vector of bools that specifies are we on the margin or not for each component. The problem, though, is that many numbers will be 0 in the actual underlying solution, but in our representation of the solution, which is approximated using jump, it will be slightly larger than 0. So what we need to do is give ourselves some slack here. And one easy way to do it is just divide eta by c, and then check whether the resulting numbers are between, let's say, 0.01 and 0.99. And this is not the most principled way to do it, but it's going to work on the data sets that we're experimenting with here. And on real problems, you'll want to use libsvm anyway. So now, to return a prediction for a particular row x, we want to follow the strategy that we outlined before. We come up with our k-test matrix, which applies a kernel function to a row from the training set and the test point x. So we do that for all the rows. That gives us a row vector. And then we multiply that row vector by eta times y, and then we add alpha to each component. And then we have this code written here for us to visualize the SVM. It's just computing suitable bounds and then plotting a heat map and a contour plot and then scattering the training observations and coloring them. The resulting fit here is very nice. It found the decision boundary that we found, but it did so without having to invoke some special algebra knowledge. Problem 3 asks us to look at the radial basis kernel on the same data set. And for this small value of gamma, what's going on is that we get a much more locally responsive model. Clearly the model is sort of feeling these data points and classifying points as blue because it's pretty close to them. And similarly for these. But somehow here in the middle it's feeling this clump of red points more than the blue points that are nearby. We'll get a better result if we lower the value of gamma because that's going to spread the blue stuff that's sitting at each blue training point and red stuff sitting at each red training point out more. And we'll get more of an averaged result. So with this small value of gamma, we get something quite a bit more sensible. We can also widen our margin by lowering the value of c. So we can actually see what's going on with more detail if we eliminate the signum function. In this plot, we're seeing some summary information where we have bigger than 1, less than -1, between -1 and 0, and between 0 and 1. There's these 4 colors. But we can decline to do that summary, and we actually see a much clearer picture of what's happening for the radial basis prediction function. What we get is a sort of blue pile at each one of these blue training points and a red pile at each one of these red training points. And in fact, the shape of this pile is exactly the shape of the Gaussian function that goes into making the radial basis function. So it looks like this. We have our blue points making Gaussian-shaped blue depressions, our red points making Gaussian-shaped peaks, and they add together to give the function whose sign we need to compute in order to classify. So everything that ends up above the z equals 0 plane in this picture gets classified as red, and everything below gets classified as blue. So we can see this picture kind of smooth out if we decrease the value of gamma. We see the bumps start sort of running into each other, and you get a smoother surface, and therefore a smoother decision function. Finally, problem 4 asks us to explain why that's true. Why do we get these little Gaussian humps if we use a Gaussian kernel? So if you recall, the function that we take the sign of to get a prediction is x beta plus alpha. And if we substitute beta as x transpose eta O dot y, then our formula becomes the test kernel matrix K times eta O dot y plus alpha. And then we can expand out this matrix product of K test with eta O dot y. And that corresponds to just multiplying corresponding pairs and adding up the results. Then by definition, the test kernel matrix has as its ith component K evaluated on X and the ith training point Xi. And then again, by definition, eta O dot y has as its ith component eta I yi. So we end up with this formula, which tells us that we get these Gaussian-shaped functions centered at Xi, which is either positive or negative, depending on the classification of the original training observation, and whose height depends on eta. So that gives us a nice interpretation for eta, finally. It's telling us how much weight we're giving that point as we try to make a decision about whether a new test point is on one side or the other of the decision boundary. So in summary, to apply the kernel trick, we replace x with phi of x in the dual SVM formulation, where phi is a map from our original feature space to another feature space. And then it turns out that the only appearance of x is in the form xx transpose, which consists of dot products of rows of x. So as long as we can compute dot products of images under phi of our rows, and that function is called k, then we can calculate the optimum point and make a decision boundary without ever having to think about the function phi. And that allows us to bring in our own functions k that we want to use, like a quadratic kernel or a radial basis function kernel, or even a linear kernel, which amounts to not using a transformation phi at all. Finally, in a special case of a result called the representer theorem, it turns out that the prediction function, before taking the sign, is equivalent to alpha plus a combination of functions of the form k of x comma xi, where xi ranges over the training observations and where the weights are +1 or -1 depending on the corresponding class of that training observation, multiplied by the weight eta obtained in the solution of the dual problem. So for example, if we use a radial basis kernel which has a Gaussian shape, then we end up with these upturned humps on the blue points and these downturned humps on the red points. And the height of each hump is dictated by the weight it got in the solution of the dual problem.